let's continue where we left off the last time. Last time we just introduced the subject. For the next few lectures, I'm going to go over elements of the orbital mechanics. And what that means, we're going to go through some equations that describe the motions of the satellite around the globe. Now, this is obviously a physics problem, and it is pretty complicated if you want to treat it in great detail. My goal here is to provide you with sufficient knowledge so that you can utilize some of the data that are available there to calculate the position of the satellite, the look angle, and the stuff that we need for what we are trying to achieve here. Now, in this section here, these next few lectures, there's a huge, I should say, difference between what's on the PowerPoint and what's in the notes. On PowerPoint, I'm just giving you summaries. There's tons of equations that lead to what I'm going to be presenting on the PowerPoint that are all in notes. So here I'm just going to be focusing on what the end results are. To properly understand these end results, I suggest you go through the notes equation by equation and make sure you follow the derivations that are presented there. And then I'll try to do quite a few examples to illustrate how some of these equations are used. So here's what we're going to cover today. I'm going to explain what Kepler's laws are. Originally they were called Kepler's laws of planetary motions because they explain how the planets move around the solar, in the solar system. The same set of equations govern the motion of the satellites around the Earth. We're going to look at what are the equations of the satellite orbits, what are some parameters that we use to describe the orbits, and then towards the end, how do we actually locate a satellite within the orbit, right? If you're let's say assigning some coordinate system, and you know when the satellite is at a given location at some given time, how do you predict the position of the satellite, sometime in advance, right? And this is very relevant for the satellites that are moving relative to the objects on the Earth. In particular, all the satellites that are not geostationary satellites, you would have to calculate the look angle towards them because their position constantly changes relative to all the objects on the ground. So here's a slide that talks a little bit about Kepler's law. Johannes Kepler published his laws in 17th century. It was a remarkable achievement because that was before the Newton, developed the theory of gravity. So his laws were essentially based on interpreting the measured data. Measured data were collected by this gentleman, Tycho Brahe. He had a very detailed measurements of the positions of the planet and how that evolves through time. And what Kepler did, based on these measurements, he actually generalized them and fit these equations without actually knowing the laws of gravity, right? Without even knowing calculus, right? That all came later. Newton tried to explain physics behind these equations, and to do that he had to invent calculus, and he had to discover gravity, and did all these remarkable things that he did just to properly explain what was formulated by Kepler. As I said, these laws were originally used to describe motions of the planets around the sun, but it's the same kind of problem as we have when we look at the satellite in the orbit of the Earth. In physics, this is referred to as two-body problem because you have two gravitational sources. One is the Earth, and the other one is the satellite, where the Earth is much bigger than the satellite. And if you neglect all the other things that are impacting the motion of these two, then you end up with these equations that we have here. The Kepler's laws are summarized in three equations here. First equation is this equation here. This one is reference to the coordinate system that I have given on these drawings here. This is where the position of the Earth, and this is where the satellite is. it turns out that the motion of the satellites around the Earth is on the elliptical path, right? So that satellites orbit the Earth on the ellipse, where the Earth is located within one focal point of the ellipse, right? The ellipse is a very, very general, I guess, very flexible, structure. A special case of the ellipse is a circle, right? Circle is ellipse with zero eccentricity. Therefore, circular orbit is one of the orbits that we're going to be dealing with. But in general, this equation in the polar coordinate describes the path of the satellite around the Earth. So that's the first Kepler law, saying that the satellites follow the elliptical path around the Earth. The second Kepler's law is saying that, literally stated from here, is that the cross product between your radius vector, essentially the vector that goes from the center of the Earth to the satellite, and the velocity of the satellite, derivative of the vector with respect to the time is the vector of velocity, is constant. Now, that's just reading this equation. Another way how you would commonly see this one stated is saying that the sector velocity of the satellite remains constant. Now, what is the sector velocity? Sector velocity is the area swept by the radius vector per unit time, right? So if you look at this radius vector, imagine it, going around this ellipse, then the area that is being swept per unit time remains constant. So when the radius vector is larger, that means the satellite needs to move slower. And then when the radius vector is smaller, which means when the satellite is closer to the Earth, the velocity of the satellite is larger. So in these areas here, the satellite moves faster. In these areas here, the satellite moves slower. But the area swept by the radius vector remains constant over time. So that's the second Kepler's law. And then the third Kepler's law comes and says that the ratio of the period of the orbit, like t is the period of this motion, how long does it take the satellite to revolve around the Earth? Ratio of the square of a period and cube of what is called semi-major axis. Semi-major axis is this axis here. If you look at ellipse, start with the circle, right? And then squish it, right? You have two axes, one that is across this narrow part, and one axis that is across this wide part. Semi-major axis is half of this distance, right? And semi-minor axis is half of this distance, right? Usually semi-major axis is denoted as A, and semi-minor axis is denoted as B. So this ratio of t squared, which is the square of the period it takes for the satellite to orbit the Earth, and the cube of semi-major axis remains constant, right? Which is also kind of directly observed from the data. So if you look at all of these three, you can see how they could be derived without actually knowing physics. All you have to do is have a lot of very accurate and painstakingly taken data points, and then enough patience to kind of put these equations through and determine that these equations fit those data points very well. And that's exactly what Kepler did. Now, with his laws of gravity, Newton was able to explain where all of this is coming from. And from this point, it's easy to see that this has to be true, but in his days, explanation for gravity didn't exist, right? As a matter of fact, we were still wondering if Earth might be center of the universe back then, right? So where the derivation of all of this equation comes, I have given very detailed derivation for it in the notes. It's not in your book, right? Your book kind of skips a lot of steps, so I had to fill them all in. But essentially, you start from stuff that you remember from elementary physics. You know that if you have a satellite and you have the Earth, and they are just left on their own, you neglect the impact of all the other gravitational forces around, then you say that the force that is experienced by the satellite is proportional to the mass of the Earth, mass of the satellite, distance to the satellite, distance by r squared. R cubed here is the square of the distance, right? And it tells you that this minus tells you that the force is pulling you down. Now, based on second Newton's law, the force is mass times acceleration. So if you put what that means, acceleration is the second derivative of your position vector with respect to time. So now if you take this here and put it on a left-hand side, and then you put this on the other side, you end up with this differential equation, which is a second-order differential equation of a vector variable, right? It's a second order because it features the second derivative with respect to time, and r has 3 coordinates, right? It's a spatial coordinate. So this is the differential equation that will give you as a solution all possible trajectories of the satellite, right, or any object in a gravitational field of the Earth, right? If something is flying around the Earth or moving around the Earth, and it's exposed to the gravitational field of the Earth, it has to follow this equation, right? And all the possible paths are going to be included as a solution to this equation. Now, constants here, g is the universal gravitational constant, me is the mass of the Earth, and mu is what is called Kepler's constant, and that's the one that Kepler determined. It is given here with appropriate units. So now, once you determine this, then you say, okay, what do I need to do? I need to solve for r. I need to solve this differential equation. And that's what I do to several pages in the notes. And after some work, here's what you determine. You determine that the solution for r has to be in this form, right? Where this p is a constant, which is given here as a squared over mu. Mu is the same as the Kepler's constant from the previous slide. And h here is the angular momentum, which is essentially product of your radius and your velocity, right? So the magnitude of that. But for any given satellite, this is p is a constant. R is the radius from the center of the Earth to the satellite, and at phi 0 is the angle in the coordinate system. So here you have elliptical coordinate system, or elliptical coordinate system with r, phi, and z, and it turns out when you go through the equations that the satellite needs to move in a plane that contains the center of the Earth. The Earth is in one of the focal points of the ellipse of the motion. So if this is the Earth and there's a satellite, this is the ellipse of the satellite motion. If you look at the plane that contains that ellipse, it goes to the center of the Earth, and the Earth is in the focal point of that ellipse. These r and phi are coordinates in this plane that contains the center of the Earth and the satellite, and the z-axis is the axis that is normal to this plane. Pay close attention. This is true always. The satellite does not have to be in equatorial plane of the Earth, right? It can be inclined orbit, but in that coordinate system now z-axis is tilted as well, right? Like this, and then r and phi are in this plane that contains the ellipse that the satellite is moving in. This parameter here is called eccentricity, and the solution for the trajectory of the satellite exists for all positive values of E. However, not all positive values of E result in a stable orbit that will kind of close on itself. if E is equal to 0, and we're going to later on find a way how you calculate E, but we start from this general solution. So this is what R is going to be as a function of phi. If E is equal to 0, you can see that this whole thing goes away, and your radius is constant. So this corresponds to a circular orbit. So as a special case here, you have a satellite that can be in a circular orbit, right? That's one of the special cases. For E between 0 and 1, we obtain stable elliptical orbits. And then for E greater or equal to 1, you end up with the orbits where the satellite motion is such that the satellite escapes the gravitational pull of the Earth. So there's a still valid trajectory that explains the path of the satellite through this gravitational field, but it never closes on itself. The satellite just comes and goes away, right? And then for E equal 1, this is parabola, and then for E greater than 1, this is hyperbola, but regardless of which one of those, this is not a stable orbit. The satellite does not revolve around the Earth. So we have essentially two kinds of stable orbits. We have circular orbits with eccentricity equal to 0, and then elliptical orbits where E is equal to 0 to 1. When Kepler analyzed the motion of the planets, planets essentially move in the orbits that are very close to circle. The eccentricity is very small. So it took a lot of very precise measurements to even detect that these are ellipses, right? When it comes to satellite, this is a design thing, and sometimes we have circular orbits, like all of our geostationary satellites are moving in circular orbits, but sometimes we have satellites that have highly inclined orbits and highly elliptical orbits, because we want them to dwell on a certain portion of the globe for a longer period of time. Right? So eccentricity can be anything, pretty much, depending on what the design of a given satellite is. This picture here kind of shows you all of these orbits. The red one is circular, the blue and green one is elliptical, and then this magenta one is for the also elliptical orbit that is very close to the escape orbit by eccentricity 0.9. So this is very eccentric orbit here. This piece of code here is a MATLAB code that helps to generate this plot. Now, I point again in notes, there's a very detailed derivation of all of this and kind of shows you how you walk and solve that second order differential equations of three coordinates, right? So you have quite a bit of work to do to get to this point. So that's how you determine what the motion is. Now, once you know that we are on an ellipse, we use certain parameters to describe this ellipse. When we say the satellite is moving on an elliptical orbit, then we have a handful of parameters that we use to describe what this orbit looks like. And they're kind of defined here. So let me walk through this and explain. There's going to be quite a few terms here, quite a few names of individual parameters. So I start by this ellipse here. As you know, in math, we define ellipse as I guess, locus of points that are at a distance from. You actually put two focal points, and then you say where are all the points where the sum of the distances to those two focal points is equal to constant. That's how we define the ellipse. So let's say I have two focal points, F and E here, and this ellipse here gives me the points such that, let's say, SE plus SF is constant, right? That's the definition of my ellipse. From what we've seen in the previous slides, the Earth is going to be located in one of the focal points of the ellipse. So that's where I fix the origin of my coordinate system that I'm going to be using to describe this motion. The X and Y axes are positioned like this. X goes through the point that is closest to the focal point. That point is referred to as perigee in satellite motion. So that's the place on the ellipse where the satellite is closer to the center of the Earth. Opposite here is called apogee. That's the that's the point on the ellipse where the distance between satellite and the Earth is the largest. R0 here is the radius vector. So this is the vector that goes from the center of the Earth, or the center of this coordinate system, to the satellite. And phi 0 is the angle in this elliptical coordinate system. In satellite terminology, this angle, I don't see it here defined, but it's called a true anomaly, right? Or just we can call it phi 0. It's the angle between the positive side of the x-axis and then the radius vector that connects the center of this coordinate system to the satellite. A is the, so you have 3 points here. You have a focal point F, focal point E, and then the center of the ellipse. This one is where, if you think of the ellipse as a square circle, that's where the center of the circle was, and it's still center of the ellipse. The distance from C to either perigee or apogee point is called semi-major axis. The width here is 2a, so the semi-major axis is this a, and then this distance here from the center to this point B is referred to as semi-minor axis, or we use D. So that's a description of the ellipse, and we frequently, in what we do, we're going to say, well, this is the time when the satellite passes through the perigee. This is the semi-major axis of the motion. This is the true anomaly, and so on and so forth. So these terms we're going to be using them through the at least first part of this course. Now, around this drawing here, we have 5 important results that we kind of going to be using over and over. The first result is a relationship between this A and P. This P and this P are different. The P over there is a lowercase p, this guy, right? The second relationship that we will have to know is the relationship between semi-minor axis D and P. The relationship between eccentricity, perigee, and apogee distance. So we will see that you can actually define eccentricity is as a function of the distance to the this distance here, distance to the perigee, and distance to the apogee, and then how you formulate the second Kepler's law and third Kepler's law based on all of these parameters here. So let me walk through this.
Quick question.
Go ahead.
Yeah, we know that EX plus FS is called a constant, right?
ES
Plus FS.
According to ES is this one,
Yeah,
and FS is this one.
it's called a constant.
Yeah, it's equal to 2A.
Yeah, how do we know that it's 2A?
How do I know that it's
2A.
It's 2A?
It's always.
It's always 2A.
Yeah.
It's always 2A. That's the ellipse. Ellipse. Let's see. How would I? It is always 2A. This is the for every point on this ellipse. The sum of these distances is 2A. Right. That's how ellipse is.
I think you can easily imagine it if you reposition satellite into point P. That way you will have 2A.
Yeah, that's we do that in just a
Yeah,
second.
but the law of ellipse says it's called a constant.
Yes.
Yeah, but the constant is now 2A in this condition. So how
Yeah,
do we?
this is that constant. It can be shown that the constant is equal to 2A. Right. That constant is 2A. Let's go to the next slide. We'll have that actually the equations that describe it. As a matter of fact, it's one of the equations on the next slide. So let's walk through some of these. Remember, there are 5 things, right? So let's go through these 5 things that we need to know. This is the same drawing that we had on the previous slide. If you look at this is A. Now this distance here is A times E, and this distance here is A times 1 minus E. We'll come to that as well. So relationship between A and P. If you look at this this equation here, you can see that 2A, which is essentially this plus this, right? has to be equal to R0 when you are at the perigee, which is this part here, and R0 when you're at the apogee, which is this part here, right? You can see that this plus this has to be equal to 2a, right? Because from here to here, it is 2a. So 2a is going to be R0 when phi 0 is equal to 0, plus R0 when phi 0 is equal to pi, right? So this is the distance at the perigee, this is the distance at the apogee. If you substitute 0 and pi into the first equation, then you get that this is p of 1 plus c, p of 1 minus c, or 2p1 minus e squared. So from here, you can get that semi-major axis can be expressed as p 1 minus e squared, or a squared over mu 1 minus e squared. P is equal to a squared over mu, right? Mu is the Kepler's constant, and h is the magnitude of the product of the radius vector and the linear velocity of the cell. So that's the first relationship that we know, is the relationship between your P, A, and E, right? Eccentricity, semi-major axis, and P. Likewise, we can derive equation that relates semi-minor axis to P and E. If you look at now, consider the point P. Now, if you put the satellite in this point and you observe the two focal points, then the distance from every focal point to P is going to be equal to A, right? Because the sum of the distance from any point on the circle to the two focal points is going to be 2A, and because this is in the middle of between the two focal points, then these two distances are the same. So from here, FP plus EP has to be equal to 2A. And then from this triangle here, the triangle CEP, you can see that B squared, which is this one here, is equal to A squared, which is this one here, and then minus E squared, A squared, which is the distance here, right? So when you put that in this equation, you get 1 minus E squared times A squared, but from here, I have that A squared is equal to P squared, 1 minus E squared, quantity squared. So when these two cancel, you get that this is the relationship. B squared is equal to P squared, 1 minus E squared. So therefore, you get the relationship of B. Or if you want to express B in terms of A, you get this relationship here. So that tells you that B, A are related, and eccentricity are related. And the larger, if eccentricity is equal to 0, you can see that B is equal to A, but for any other eccentricity, then B becomes smaller than A. Now, that's the second equation that we're going to be using. The third equation establishes the relationship between eccentricity, distance to the perigee, this distance from E to B, and distance to the apogee, which is the distance between E and A. From EB, which is this distance, is obtained directly from this equation for phi 0 equal to 0, right? That's the distance, that's R0 when phi 0 is equal to 0, is exactly this relationship. That's the distance to the perigee. So when you put phi 0 equal to 0, you get that P1 plus E is equal to RP. Now if you put phi 0 equal to pi, you are all the way on the other side. You get to the apogee distance. And that distance is P over 1 minus E, because cosine of the pi is minus 1. So this is R apogee. If you express now, if you look at this equation and these two equations, and you express E from there, you get that your eccentricity can be expressed as distance to the apogee minus distance to the perigee over the sum of the two distances. So that's the third very useful relationship that tells us, how you can express the eccentricity in terms of these two distances. Of course, if you have a circular orbit, these two are the same, so the eccentricity is equal to 0. And let me go through the remaining two. The second Kepler's law, what did we say about the second Kepler's law? We said that the sector velocity needs to be constant. So how do I express that one? Well, what is the sector? What is the area swept by a radius vector? It's this elementary area dA. I can express this area as, if you think of this as a little triangle, so you can say that this is 1/2 of this R0 times this ds times the sine of the angle between these two, right? Or the easiest way to see this is the magnitude of the cross product between R0 and let me see here, R0 ds. Oh, okay, v dt is the ds, right? The velocity, the linear velocity of the satellite dt is essentially this ds. So if you look at now what this translates is to 1/2 cross product between R0, which is the radius vector, and the linear velocity times the dt. And then if you divide these two, you get that dA over dt, which is what we call sector velocity, essentially how much of the area is swept over unit time, is equal to 1/2 R0 cross dR0 over dt. In the notes, it is shown that this quantity has to be constant, and this is equal to this h. So the sector velocity is dA over dt, and it has to be constant. Now this is a little bit intermediary result. I mean, it's not as much used as the other ones that I show you, like the first three, but it's used to derive this very important one, which is the third Kepler's law. If you now start from this one here, and you say, okay, well, dA is equal to 1/2 h dt, and you integrate over one period. Then if I integrate left-hand side over one period, I get the total ellipse, right? Because this is the area that is swept over one period is the total ellipse. The area of the ellipse is P times A times B, right? And then here I integrate 1 over 2, 0 to T, where T is the period, h dt. Well, h is the constant, right? So this is 1/2 h dt. Now, if you look at from here, I can express T, and if I square it, and I use my relationship for A and B, and that I have derived on a previous slide. As a matter of fact, I just used the relationship for B. Then I have that the T squared is equal to 4 pi. That's this 2, and this pi gives me 4 pi. A squared, then B is squared is this part here, divided by A squared is equal to this T squared. Well, if I now group the factors and interpret, I guess, take one of these A's and this eccentricity here and make that this P, and then 4 pi squared and A squared. And when the clutter a little bit clears, what I end up here is that T squared is equal to some constant here. You can see that this is a constant for a given trajectory, and then I have A cubed. So therefore, this is where the third Kepler law is coming from, saying that the square of the period and the cube of the semi-major axis are directly proportional. Now, this can be simplified somewhat because this h squared over p is essentially mu, where mu is that Kepler's constant. So all of these are constants, right? P is our 3.14, and this mu is that 3.86 that times 10 to the 5, which is Kepler's constant. So we get this important relationship that P squared and A cubed are related. So those are the 5 things that we need to know when we are describing the ellipse. The first 3 we're going to be using in quite a few equations, and then the 5th one we're going to be using as well quite often. This one is important to know, important to understand, but it is usually used indirectly for the third Kepler. All right. So now the question is, how do you determine the position of the satellite, right? Let's say you know that it passes at let's say midnight, it's going to pass through the perigee, and then you wonder, how do I calculate its positions 3 hours from that point, right? And the question is somewhat not easy to answer if you try to rely on these elliptical coordinate systems. Because one thing that you probably, I don't know if you notice, all of these equations here give us just the relationships, geometrical relationship. There is t missing from all of these equations except maybe this one here. So you know the path, right? But the velocity of the satellite changes on the path, right? And it remember, it's faster in around perigee and it's slower around the apogee. So it's relatively complicated to calculate the position of the satellite if you try to follow the differential equations on their own. So in the notes there is derivations that justify the process that I'm going to kind of summarize here. And this is the process that allows me to calculate position of the satellite on this in this coordinate system based on some defined parameters. And I'll give you a process, and then we're going to walk through an example that shows you how you actually calculate with some particular numbers and how you actually do these calculations. Now, this process is I would say, simplified method of doing it. There's justification and there's a detailed derivation for why this works given the notes. But what I'm going to do here is just summarize and give you an example of how this is done. So here's what I'm going to assume, that we know the time at perigee. We know when the satellite goes through the position where it's closest to the Earth. And usually that time for all the satellites, we'll cover something that's called two-line data. But in general, that's one of the parameters that is specified for any satellite. When is it closest to the Earth? And that's kind of used as a reference point. And the task here is to determine the location of the satellite for an arbitrary time after that particular point. So I can say satellite passed through the perigee at noon. Where is it going to be, 3 hours from that point, right? And when I say where is it going to be, what I really need to determine, either its XY coordinate or its R0, phi coordinate, right? R0, phi, 0 coordinate. XY coordinate will give me the position of the satellite in a rectangular coordinate system, and R0, phi will give me the same position, but now in a cylindrical coordinate system. This coordinate system that I'm talking about here is the one that is traveling with attached to the satellite. This one is containing the trajectory of the satellite as an XY plane. Right? So for every satellite, this coordinate system is different. Right? And we'll show later how we actually moved it to the same coordinate system for all the satellites. So referencing back to this figure here, I define S is the position of the satellite. This is what I'm trying to express, to determine where this point is sometime t that is greater than tp. O here is the center of the Earth. That's the center of my coordinate system. X and Y is the plane that contains the ellipse that the satellite moves on. Z-axis is coming right out of the board, right? That's the axis that is normal to the plane that contains the path of the satellite. C here is the center of the ellipse, right? So that's halfway between the two focal points of this particular ellipse. R0 and phi 0 are the cylindrical coordinates of the satellite, right? The satellite moves in this plane here, xy, but I can express its position by either giving you x and y coordinate or giving you r and phi coordinate, right? They're equivalent, right? Just different coordinate system. In satellite terminology, this phi 0 angle is called true anomaly. So that's what we covered so far. This is kind of what exists. Here's what we define now. What I'm going to do is I'm going to draw a circle that contains this ellipse. The circle will have the same center as the ellipse. It will have the radius equal to the semi-major axis of this ellipse. So it will touch the ellipse here, and it will touch the ellipse here. and it will kind of encompass the entire ellipse, right? Everywhere else, this circle is going to be larger than the ellipse, right? Because it's kind of touching it here and here at the 2 points where the ellipse is the value of the ellipse is the largest. Now, I'm going to define an angle E that is the angle between the positive side of the x-axis and the projection of the satellite on this circle, right? So what do? I take the satellite point, I draw a vertical through this point until it hits this circle. A is the point where it hits the circle, and I define this angle E. This is called eccentric anomaly, this particular angle. Why is this angle important to us? Because it turns out it is easy to calculate, right? So we're going to be able to easily calculate this angle, and then by knowing this angle, we'll go back and calculate R0 and phi0. So what is E? It's the angle between the positive side of the x-axis and this point A, which I have obtained as a projection of the satellite point onto this circle that encompasses this ellipse. The second thing I define is the average angular velocity. What is the average angular velocity? Well, over one period, the satellite traverses 2 pi, right? For the period of its revolution around the Earth. What is the angle that it goes? 360 degrees or 2 pi, right? Well, 2 pi over t is the average angular velocity. The satellite moves at different angular velocities as it goes on this ellipse, but on average it will cover the angle of 2 pi over the period of t, right? Now, this can be expressed, remember t and a are related quantities, so I can express this average angular velocity either by expressing it through t, or because t and a are proportional based on a third Kepler's law, I can go to the equation for the third Kepler's law, express t in terms of a, and get to this equation here. So I can express this average angular velocity by either through the period or through the semi-major axis. And then the last thing I'm going to define is what is called mean anomaly. And mean anomaly is, imagine this satellite traveling at this average angular velocity for a given time t, right? So that's where, on average, this satellite would be, right? This is the angle here. It's not any particular angle. It's just this angular velocity times the time that elapses between the current time that I'm looking at and the time at the page. So this is mean anomaly, average angular velocity, and eccentricity. Eccentric anomaly, sorry, not eccentric. So based on these definitions, here's the process that I have to calculate the position of the satellite. First thing, based on semi-major axis of the satellite, or period, I can go to the other equation and express this in terms of period. This is, if I know period, then eta is 2 pi over t. If I know a, then eta is calculated this way. So to calculate the position of the satellite, first I calculate average angular velocity. Then, based on the time for which I want to do the calculations, I can calculate mean anomaly using this equation here. Once I know mean anomaly and eccentricity of my satellite orbit, I can calculate eccentric anomaly by solving for E from this equation. Once I know E, then I can easily express R0 and phi0. And once I know R0 and phi0, I can calculate the rectangular coordinates. So that's the process. It's relatively straightforward. It has only one tricky part. What is the tricky part? This equation here. Because this equation here has to be solved numerically. Right? You cannot really express E here, solve for E from this equation. You have to do that iteratively. And I'll show you in just a second how you go about doing it. So if I know what is the orbit of the satellite, and how do I know the orbit of the satellite? I know one of its parameters. For example, I know its semi-major axis, and I know its period, right? And I know the time through perigee. Then I can calculate the position of the satellite on that orbit at any given time using this particular set of equations. So we're going to go through an example in just a second. So let me go through an example of some of these calculations. What I'll do is I'll turn this thing off, and we'll go. And I'll walk you through several examples. All right, so this is this. Before I go there, let me do a couple of simpler examples, and then we'll go to this one. Let me go through a first example. And this is the same as example 2.1.1 in the textbook. It says this: Earth rotation for the period of the Earth rotation is equal to 23 hours, 56 minutes, and 4.09 seconds. So this is how long does it take for Earth to rotate around its axis. So if this is a rotation time of the Earth, determine the radius to a geostationary satellite. Right? How far does the geostationary satellite needs to be so that it is completely synchronous with the Earth, so that we see it always from the same at the same point in the sky. If I look the Earth from the North Pole, right, or from the above, so to speak, although in space there's no above and below, but if I look at it from the pole, here's where geosynchronous satellite is going to be. It's going to be at some distance r0, and its rotation, let's say, move this way. The rotation is going to be such that it is always on the same point in the sky from somebody viewing it from the Earth. So if I look at this now, what should be the period of this satellite in its orbit? First, it has to be in a circular orbit, right? And then the second thing, it needs to have the period that is exactly this, right? So now, how do I determine the radius to the satellite? Well, radius in this case is going to be the same as the semi-major, or for that matter, semi-minor axis of the ellipse, because ellipse is a circle here. And third Kepler's law will give me the relationship between this period and semi-major axis, right? We know that the square of the period is proportional to the cube of the semi-major axis, or in this case, the cube of the radius to this satellite. So the first thing I'm going to do is I'm going to calculate this period in seconds. So this is 23 times 60 to get it in minutes, plus 56 minutes times 60 to get it in seconds, and plus 4.09. So this is 86, 164, 09 seconds. So this is exactly the period of the Earth rotation. And we know that A, or let me just go back to the Kepler's law that says that T squared is equal to 4 pi squared over mu times A cubed, right? That's third Kepler's law. So from here, I can express A as being mu T squared over 4 pi squared, taken third root from that. And if I substitute now the numerical values, this becomes 3.986 times 10 to the 14 meters cubed over second square. So this is the value of the Kepler's constant, times 8616409 quantity squared, I guess second squared, and then divide here by 4 pi squared, right, taking the third root, right? So this would give me the distance in and when I do the calculations, this is 42164.17 kilometers. So roughly 42,000 kilometers, from which point? From the center of the Earth, right? How much is that from the surface of the Earth, right? We have, those are the two things that are commonly, referenced. You got to be careful when you're doing problems, which one are you really calculating here. When I calculate it this way, I'm calculating from the center of the Earth, or from the center of the coordinate system to the satellite. But the Earth extends certain distance. The radius of the Earth is 6,384 kilometers, roughly, right? Depending, if you assume it's sphere, Earth is slightly, has a bulge around the belly. But this is an average radius of the Earth. So a lot of times when they talk about satellites, geostationary satellites, they don't give you the distance from the center of the Earth, but rather they give you the altitude. How high is the satellite above the surface of the Earth? So the height of the satellite, or the altitude of the satellite, is going to be this R0 minus radius of the Earth. And this is, in this case, 42,164.17 minus 6,384, all that in kilometers. And this gives you an altitude of 3517 kilometers, roughly 36,000 kilometers. So you will find in literature both of these numbers, 42,000 kilometers, which is the distance from the center of the Earth, or 36,000 kilometers, which is the actual altitude of the satellite, above the surface of the Earth. Okay? And this satellite will be, as I said, on a path that is geostationary path. It will sit on the equatorial plane, and it will move in such a fashion that it's always seen in the same spot when you view it from the ground. All right, so let's take a look at another example. So this example is now low orbiting satellite, LEO satellite, and this is example 2.12. It's related to a space shuttle. So here's what we assume, that altitude which I call here D, is 250 kilometers. So you can see this satellite is very, very close to the ground, right? It is in a low orbit. It's still, in the atmosphere, right? This is where you still experience some drag from the atmosphere. What we also know that it moves in a circular orbit. And it says here, determine T, which is the period, of the orbit, linear velocity, of this satellite, and angular velocity. Now, since you're moving here on a circular orbit, your angular velocity is the same as average angular velocity, because you're always moving at a constant speed. Right? So let's calculate first the period. We know that the t squared is equal to 4 pi squared over mu times a cubed. But a is going to be equal to your altitude plus the radius of the Earth, right? Because the a is the distance from the center of the coordinate system, which is placed in the center of the Earth. So here we have that this is equal to 6378.14. I guess here R E is equal to 6378.14. And then plus 250, everything in kilometers. And this gives you the radius of the ellipse or the circular orbit is 6628.14 kilometers. So this is how far this particular satellite is from the center of the coordinate system, which is placed in the center of the Earth. So from here, once you know the A, you can calculate T easily. So T, I guess here, becomes, let me just do it this way, 4 pi squared over mu. Mu is 3.986 times 10 to the 14 meters cubed over second squared. And then times this distance here, so this is 6628.14 times 10 to the 3 in cube meters cubed, right? And then you have to take the square root of that, and you get about 90 minutes. It's 89.5 minutes, roughly 1.8 hours. So how long does it take for the satellite to orbit the Earth? About 90 minutes. It's moving really fast, right? If you think about it, you know, it is about the same location every 1.5 hours. The same location in space. You have to also take into account that the Earth is not rotating, so it's not in the same spot from the Earth. So this is the first answer. What's the linear velocity? Well, linear velocity is essentially the length of the trajectory that it goes divided by this period. So I can calculate the linear velocity as 2 pi times a divided by this period, right? Because it makes a circle, which is 2 pi a over the period that is 89.5 minutes. So if you calculate this is 2 pi times 6628.14 kilometers divided by 89.5 times 60 in seconds, right? So when you calculate this, this ends up being 7.8 kilometers per second. And that is kind of what I had on the slide from the last time. For low orbiting satellites, they're around 7.8 kilometers per second. That's their linear velocity. So in 1 second, it goes close to 8 kilometers, just to not fall on the Earth. And then the last calculation here, what's the angular velocity? Angular velocity is going to be 2 pi over t. So it's going to be 2 pi divided by 89.5 times 60 seconds. So this ends up being 1.17 milliradians per second, or which is approximately 4.02 degrees per second. So it is zooming 4 degrees. Oh no, sorry, not this fast. For 4 degrees per minute. Right? Every minute it traverses 4 degrees on the sky. So that's where the reason why I did this example is to give you some boundaries. ranges, right? If you look at, this is as far as you can go in space. We deploy the satellites that are geostationary. They're the furthest satellites we usually deploy. And then the smaller, the closest to the ground are these low Earth orbiting satellites that are just barely out of the atmosphere. All the other satellites are going to be in between these two extremes. Okay, so let me actually do, I'm going to skip this example so that I can do the other one. So let me go back to the calculation of the satellite within its orbit, satellite position within its orbit. So this is, it says example, it says C1. I don't know what C1 means, if it's even, it's been some time since I put this on paper, so it might be something referencing to what's on the book or maybe. So, but it says consider the satellite with following parameters. A is given as 22,164 kilometers. So this is a medium Earth orbiting satellite. It's MEO orbit. It has eccentricity E equal to 0.02. And it says determine the position of the satellite in its orbit 4 and 24 hours after passing through perigee. So T1 is equal to 4 hours and T2 is 24 hours. Now, if you think about, I don't know if you can see that right away, but you remember satellite, the period of the satellite, we will actually calculate it, but it has to be between 1.5 hours and less than 23 hours, 23, 56, 4.09, right? So that's the two boundaries. So here, at this distance, you probably haven't made, in 4 hours, you haven't made a single period, right? But here, at this time, you probably went through a couple of those periods because your period is smaller than, your distance is smaller than the geostationary distance, and your time is larger than the geostationary time, right? So that's why these two times are here. So what is the process? And remember, there are several steps to the process of calculation of the position. Actually, there are 5 steps. In the first step, we calculate mean angular velocity or average angular velocity. So calculate average angular velocity. We said this angular velocity can be calculated as 2 pi over the period, right? Because over one period you traverse 2 pi angle, but because the period is related to the semi-major axis, the square of the period is related to the cube of the semi-major axis, we actually can express this as mu 1/2 divided by a 3/2. Right, where mu is the Kepler's constant and a is the semi-major axis of the ellipse associated with the satellite. So in this case, this becomes 3.986 times 10 to the 14 meters cubed per second squared, taken 1/2 of that, and then divide by 22,164 times 10 to the 3 meters, 3 halves of that, right? And when you do the calculations, you end up that this velocity, this average angular velocity is 0.1913 times 10 to the minus 3 radians per second. Just for your reference, you've seen that the fastest we can go is 1.2 milliradians per second. So this angular velocity is always going to be in milliradians per second. The previous example was the fastest, the LEO satellite, right? So that's your first step, your average angular velocity. The second step is you calculate your mean anomaly. So I have two times here, 4 and 24. So I'm going to say N4, which is anomaly after 4 hours, is going to be N eta T1 minus T perigee, which is essentially this 4 hours. This is after perigee, after passing the perigee. So this gives me a mean anomaly of 0.1913 times 10 to the minus 3 radians per second times 4 times 3600 seconds, right? Because an hour has 3600 seconds. 4 hours is 4 times that. So this gives me an angle of 2.7547 radians. So this is how much of a mean anomaly I have over this period of 4 hours. Now, M24 is going to be nu T2 minus the time of perigee, which is the same 1913 times 10 to the minus 3 radian per second times 24 times 3600 in seconds. So when you calculate this, this gives you 16.5283 radians. Now this is obviously more than the 2 pi. Go ahead.
Your CP, is it always going to be 0? Or should it be
This is the delta t, right? Delta t, the time after perigee. You know, the time, is it always going to be 0? Depends what is it that if I give it, if I pass through perigee, I can give you the time. Let's say it is noon today, right? So it's not 0. But what I'm doing when I'm calculating the position of the satellite, I'm calculating relative to that time where it passed through perigee. At TP, I know where the satellite is. It is at the perigee of the ellipse. And then I'm wondering at some later time where exactly the satellite is going to be. Right? So when I gave you here time T1, what I'm really giving you is, you know, delta T, right? I'm a little bit misrepresented this. This is the time that elapsed since passage through perigee. All right, so now if you look at this, this is more than 2 pi. As a matter of fact, it's quite a bit more than 2 pi. So you made several full rotations here. And you can see that this is 2 times 2 pi plus 3.9619 radians. So you made 2 full rotations plus some more in 24 hours. Right? Now, the tricky part. Once you know your mean anomaly, we have to calculate the capital E, eccentric anomaly. And that one is calculated from this equation. So at T equal 4 hours after perigee, we have the following. We have M, let me just write the general equation. The equation that we use for calculating eccentric anomaly is this one. M is equal E minus E sine of E. From this equation, I need to calculate what E is. Right? And let me just give results here, and then I'll comment how you actually do them. So for T1 of 4 hours, I have the following. M is equal to 2.7, 7547. This has to be equal to E minus 0.02 times sine of E. And when you calculate what E is, this gives you E4 equal to 2.7621 radian. And if I look at the other time, T2, which is 24 hours, then I can neglect all of these multiples of the 2 pi. They don't do anything. It's just full circle, right? I passed through perigee multiple times. So I can just work with this number here. So this is 3.9619 is equal to E minus 0.02 sine of E. And when you calculate how large E is from here, you get E24 equal to 3.9475 radian. And so those are the two eccentric anomalies. Once you know E, then you can easily calculate the positions of the satellite in either rectangular or elliptical coordinates. So this is position of the satellite in polar coordinates. You can say R for 0, 4. This is equal to, I gave you those equations on the slide. Let's see if I have them here. Is equal to A1 minus E cosine of E. So in our case here, this becomes 22,164 times 1 minus 0.02 times cosine of 2.7621 radians, and this gives you 22,575.74 kilometers. So this is how far the satellite is going to be. What is more interesting is at what angle we should look at for satellite, and this is given as inverse cosine of A1 minus E squared minus R0 over R0 times E. And that's the equation that will give me the distance to the angular distance to the satellite. And if I substitute the values here, this becomes cosine inverse of 22,164. 1 minus 0.02 squared minus 22,575.74 divided by 0.02 times 22,575.74. And this gives you an angle of 2.7694 radians. So that's where the satellite is. If you were to draw it, this is your x0, y0. This is the direction to the perigee. And let's say this is your ellipse of the satellite. This is where the Earth is. And I kind of a little bit, I should maybe exaggerate because make it a little bit more of an ellipse. So if you look at angularly, you're going to be at 2 point, so this is pi, so you're going to be in this direction. So the satellite is going to be somewhere here. Right? This angle here is going to be 2.7694 radians. and this distance is going to be 22,000 kilometers. And there is a calculation for the other time as well. Now, the one thing that I want to address is, here I kind of skipped that step. I said, well, let's see that this is equation, right? And I somehow solve it. Right? How do I solve this equation? My calculator does it for me. If you don't have a good calculator, here's a procedure that you can do. So solving for eccentric anomaly. So here's the equation that we start with. We say m is equal to e minus e, what is the sine of e. So here I can take this e on this other side and then say e is equal to m plus e sine of e. Right? Just a simple manipulation of this equation here. You have to remember, in most circumstances, e is relatively small, right? So if the e is relatively small, you can see in the first approximation, these two numbers have to be close to 1, right? E and m are close to 1. If you look at my solution here, m was 2.7547, and the solution was 2.7621. So what I do from this standpoint, I can form an iterative process. And I can say, well, let's iterative procedure. I say my E of 0 is equal to m, right? So I start by guessing that my eccentric anomaly is the same as my mean anomaly, right? It's not, but it's close, right? And then I can say A E of k plus 1 is equal to m plus E sine of E of k. So I get a better estimate of E by plugging the previous estimate into this equation. And I keep on doing that until E converges. Do you follow? Let me give you a numerical example. Let's look at solution. Let's look at what happens in this case. So example. I start with the equation 3.9619 is equal to E minus 0.02 times sine of E. So I need to solve this equation. So I start by saying E of 0 is equal to this, 3.9619. And then I form an iterative procedure that says E of k plus 1 is equal to 3.9619 plus E sine of E of k. That's my iterative procedure. And let me just do here k equal 1, k equal 2, k equal 3, and so on. So k equal 1 says E of 1, my first estimate is going to be 3.9619 plus E times sine of E of 0, right? So I would have E of 1 equal to 3.9619 plus 0.02 times sine. What is my E of 0? This, right? My first guess. So 3.9619. And when you do the calculations, you get that this is 3.9473. And now you plug this one to get the next estimate. So this becomes 3.9475. And this becomes 3.9475. So in 3 iterations, you get to the solution, right? So it's relatively fast convergence for small e. If e is small, you get there relatively fast. And what you can do is you can write a simple Excel or write a simple MATLAB just to do these calculations. Okay? So what is it that we determine? If we know the time through perigee, and we know the parameters of the ellipse, we can actually, we have a process, this 5-step process, that will allow us to tell exactly where the satellite is on this particular orbit. The problem with these calculations is that they're orbit specific. So every satellite has its own orbit, right? Because if nothing else, even if they're all in the same plane, they may have perigee at different points, right? So we now need to find a way how to take the position of the satellite from this, I guess, orbit-specific coordinate system and put it into something that is kind of universal. And we're going to have a geocentric system, and then ultimately we're going to look at latitude and longitude, this system that we use, right? And then based on that, we'll be able to kind of sitting at a given latitude and longitude say it's in this direction. But that's going to be covered next time. All right, so that's what I kind of managed for today. There's way more in the notes. This is probably, as I said, one of the lectures where there's way more in the notes than what I cover in slides. Make sure you have a weekend, go through the notes, make sure you kind of understand this. There's a lot of stuff that you might have seen sometimes in physics, but it was a long time ago. So, all right.